Yeah, welcome. So, in the last lecture, we have discussed about deadlock. We defined what is a deadlock and under which situation deadlock occurs, and uh, and how to detect a deadlock using DAG. Uh, sorry, how to detect a deadlock using resource allocation graph. That's what we have discussed in the last session. So, in this lecture, we'll be discussing the various methods for handling deadlocks. So there are three things we can do with the deadlock. The first is we can prevent the deadlock. We can we can prevent the deadlock. That means we can ensure that a deadlock never happens. Okay. So there are two techniques to make sure that deadlock the system will never enter to a state of deadlock, and these are called as deadlock prevention technique and deadlock avoidance technique. So basically, we have two techniques to make sure that the system will never enter into a state of deadlock. Okay, and then we have deadlock recovery. It means you allow the system to enter to the deadlock and then recover from that. So that is called as deadlock recovery. And the third option is you pretend as if deadlock has not at all occurred and you ignore that problem itself. So these are the three ways of handling the deadlock. The first method is preventing or avoiding the deadlock. That is to make sure that the system will never enter into a deadlock state. And the second method is to allow the system to enter the deadlock state and then to recover from that. And the third method is to ignore the problem itself and to pretend as if deadlock has not at all happened. So you might be wondering about the third case, how it will work. But in most cases, the third method is also fine because deadlock is not a situation where a computer will encounter frequently. It is a rare occurrence. So the system may enter into a deadlock state maybe once in a year or or twice in a year. So it is so if you ignore it, it is not going to be a big loss or anything. Rather, if you want to implement some deadlock detection or prevention or recovery algorithm, then the cost involved in that may be very high. Okay, so it all depends on what is the level of usage of your system, whether you are using for corporate purpose or for personal purpose. So considering that, ignoring the deadlock is also one of the option. So in this lecture, we'll be discussing about deadlock prevention. How to prevent the deadlock. So in the previous lecture, we have discussed the necessary conditions for deadlock. So there are four necessary conditions for deadlock. So if you could recollect, the four necessary conditions for deadlock were mutual exclusion. That is, at least one of the process should be in the critical section, so that other processes were waiting to enter the critical section. And the second is hold and wait. That is that is the processes where holding one resource and they are waiting for some other resource. And no preemption. That's the third condition. That is, the resources cannot be forcibly removed from the process. And then circular wait, which means every process is waiting for some other resource which is held by the other process. So only if all these four conditions are satisfied, the system will enter into a deadlock state. So preventing the deadlock prevention technique, what it says in the sense, you make sure that at least one of these condition is not satisfied. The deadlock prevention technique says that make sure that at least one of these condition is not satisfied. So if you ensure that at least one of the condition is not satisfied, then your system will not enter into a deadlock state. Okay. So let us see how that can be done. So the first is mutual exclusion. So how can we avoid mutual exclusion? How could we? What is the under which situation you can say that the process need not enter the mutual exclusion. So the question of mutual exclusion comes with a shared resource. The question of mutual exclusion comes with a shared resource. So if we have a shared resource, then sorry, yeah, if there is a shared resource and there are more than one process want to access this shared resource, then these process cannot access the shared resource simultaneously. Only one process can access. If one process is accessing, then all other process should be waiting. This is the idea of mutual exclusion. Okay, but assume that this shared resource is a read-only file. Assume that this shared resource is a read-only file. That is, it is a file which the process can perform only a read operation. They cannot write it. Okay, in that case, if the shared resource is a read-only resource, then actually you need not follow the concept of mutual exclusion. Then you can allow all the process to access the shared resource simultaneously, because it is a read-only resource and nobody is going to tamper the resource. There is no possibility of tampering the resource. Okay, so this is one of the way how mutual exclusion can be avoided. Okay, because if mutual exclusion is avoided, then there is no deadlock. So so the operating systems should see the type of the resource, type of the shared resource. It should not enforce mutual exclusion for all the shared resource. If the shared resource is a read-only resource, then multiple process can access the read-only resource at the same time. So this is how the condition of mutual exclusion can be avoided. Okay. The next is hold and wait. Okay. So hold and wait, what it says, the logic of hold and wait is all the process is holding one resource and they are waiting for another resource. Or here we are talking about individual process. If you take an individual process, it is holding one resource and it is waiting for uh, another resource. So so the so the concept of hold and wait here what we discuss in the sense how to avoid hold and wait. Okay. So hold and wait can be avoided by following one particular approach. That is, the process should request all the resource whatever it want before the execution begins. Okay. If a say there is a process pi, and the process pi during its lifetime, it may require 5 resource, 6 resource, or 10 resource, whatever it may be. So what are the resources it is going to use? So before the execution begins, it should request all the resource and it should get the resource and then it should start. Okay. If that condition is there, then never hold and wait will occur, because before starting itself, the process is acquiring all the resource and it is working. Okay. Or if it fails to do so, okay, say the process is not doing that, then say the process is already holding some resource. pi is holding, say, some 2 resource, but after some times, after after say x milliseconds, it is again asking for another 3 resources. In that case, the operating system should ensure that first the process let first the process give up all the resource. First the process give up all the resource, then only it can request for new resource. Okay. The process can request new resource only if the process has no resources allocated to it. So by following these two conditions, hold and wait can be avoided. The first rule says that before beginning the execution itself, the process should execute all the resources. The second rule says that if at all the process wants further new resources, then at that particular time it should not be having any other resource. This is how hold and wait can be avoided. But by enforcing to avoid hold and wait, it may lead to low resource utilization and starvation. It may also lead to starvation. but it will avoid deadlock. So mutual exclusion can be avoided by allowing all process to access the shared data simultaneously if the shared data is a read-only data. And hold and wait can be avoided by ensuring these two rules. The first rule is that the process should request all resource before the execution starts. And the second rule is that if at all it wants some new resource, then it can request new resource only if it is currently not holding any other resources. The third is no preemption. So, so no preemption means the operating system cannot forcibly take away any process, any resource from a process. So how can this condition, how can we avoid this condition? Okay, so assume the process is holding some resource. Assume the process is holding some resource, and it is requesting for new resource. The process is holding some resource, and it is requesting for some other resource which cannot be currently allocated. Which cannot be currently allocated because that resource may be allocated to some other process. Okay, so then the process should voluntarily give up all its resources. Then the process should voluntarily release all the resource, because by default it is no preemption. The operating system cannot forcibly uh, remove the remove the resources from the process. Okay, so here the first rule says that if a process is requesting for new resource, already it is also holding some resource and it is requesting for new resource, and that request, if it cannot be satisfied by the operating system at the particular time, then that process should voluntarily release all the resources that it is holding. Okay, so all the resources whatever it released, and whatever the preempted resources means whatever the release, whatever the resources that the process has recently released, as it is unavailable to, as it is not able to get the new resources. So those resources are the preempted resources. The preempted resources will also be added to the list of the waiting resources along with the other new resources whatever it want. Okay, and the process will be started only when all the resources are available. Process will be started only when it can get all its resources. So this condition is called as preemption. So this is how we can avoid preemption. This is how we can avoid preemption. That is, if a process is currently holding some resource and if it is requesting for new resource, and if that new resource cannot be allocated, then the process should voluntarily give up all the resource that it is holding. So all the resource that it is currently recently released, that resource, say recently it released some X resource, and further it is waiting for some Y resources. All those resources will be added to the list of the resource for which the process is waiting. And the process will be once again restarted only if all these X plus Y resources are available at the same time. Until then, it will be waiting. So if these rules are followed, then uh, then the then the preemption can be avoided. Okay. So why we want to avoid in the sense, because by avoiding any one of these things, deadlock can be prevented. The fourth condition for deadlock is circular wait. So how to avoid circular wait? Circular wait, again, circular wait can be avoided by numbering the resources. First, impose a strict ordering or total ordering of all resource types. We, we, we give some ordering on all resource types, and then process request to the resource will be satisfied by an increasing order of enumeration. Process request to the resource will be satisfied by an increasing order of enumeration. So what does it mean? What does it mean? Okay, so let us try to understand how to avoid circular wait with some example. 1 minute. Okay, so let us So let us assume that we have some functions. Okay, say f of td. Okay, td represents tape drive. Okay, td represents tape drive. Okay, so f of td is equal to 1, which means currently my system is having one tape drive. Okay, tape drive is something like a CD drive which is used to play video or audio tapes. Okay, and then I have something, and then I have f of, so so we are discussing about how to avoid circular weight. So this is the algorithm or the logic. Say we have f of disk drive. Okay, so f of dd, so td represents tape drive and dd represents disk drive. Say f of dd is equal to 5. It means currently my system is having 5 disk drives. Okay, and then say f of p, which means printer. F of p is printer. It means my system is having 12 printers. It means 12 printers. Okay, the system which I am using is having these resources: tape drives 1, and disk drives 5, and printer 12. Okay, okay. Now, how to avoid circular weight? In the sense, the process should request resources in an increasing order of enumeration. Okay, fine. So let us assume the process pi. Okay, let us assume the process pi, and assume the process pi is already holding a resource. So initially, when the process pi is asks for some resource for the first time, initially any process pi, when it asks for a resource for the first time, whatever the resource it requests, it will be allocated, provided it is available. Provided it is available, all the resource whatever it requests, it will be allocated in the first time. Okay, so let us assume pi was initially allocated with the resource ri. Pi is initially allocated with the resource ri. Okay, then say after some times, pi is requesting for another resource. So this is initially pi is allocated with the resource ri. Then after say x amount of time, pi is requesting for another resource rj. pi is requesting for another resource rj. Okay, now rj will be allocated to uh, the process pi. Now rj will be allocated to the process pi only if f of rj, only if f of rj is greater than f of ri. Okay, only if f of rj is greater than f of ri. Okay, otherwise, even if some instances of rj is available, it won't be allocated. It won't be allocated. Okay, then the process should release ri, and then first it should take rj, and then it should take ri. Okay, so the rule says that initially when a process pi requests for any resource, the resource will be allocated as such. But the second time, if it requests for a resource, then it will check like uh, f of rj, that is the new resource it is requesting, whether 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 the number of instances available for f of rj is greater than f of ri or not. Only if it is greater than, it will be allocated. Otherwise, it won't be allocated. Okay. So in this case, if assume that pi is requesting for tape drive and printer. Okay, tape drive and printer. Then first it should request tape drive, and then it should request printer. Only if it follows this order, it will be allocated. Okay, if it follows the reverse order, uh, then it won't be allocated. Okay, so in this case, what is uh, tape drive? What is f of td? F of td is 1. So this 1 is nothing but ri. This 1 is nothing but ri. Okay, and what is f of p? F of p is 12. So this 12 is nothing but rj. Okay, so initially when it requests for tape drive, it will be allocated, ri is allocated. But next time when it requests for the printer, it will check that f of rj, f of here printer, f of rj is 12, is it greater than f of Ri? Yes, it is greater than, so it will be allocated. Otherwise, it won't be allocated. Okay. For example, if the process is first requesting for printer and then requesting for the tape drive, means it won't be allocated, and it will be asked to remove. Then it won't be allocated. Then it should first give up the printer. First, it should give up the printer, and it should follow the increasing order of enumeration. That is, first it should request for the devices which are available in less instances, and then it should request for the devices which are available in more instances. So by following this ordering, we can ensure that circular wait can be uh, uh, avoided. Okay. So so this is what deadlock prevention technique is about. Okay. So basically, deadlock can be prevented by making sure that any one of the necessary condition of deadlock doesn't exist. That is, mutual exclusion, uh, or hold and wait, or no preemption, or circular wait. And this is how, and we have discussed various ways how this can be avoided. Okay, fine. So in this video, basically we have discussed what are the ways of handling deadlock. So there are three ways. Either you can avoid the deadlock, I mean, before deadlock occurs itself, you can avoid it by using two techniques: deadlock prevention technique and avoiding technique. And then you can recover from the deadlock by allowing it to happen. The third is ignore the deadlock. So here we have discussed about preventing the deadlock, how deadlock can be prevented. Thank you.